Is just one of those extra days that because we got done before the main section, and we'll be doing an extra topic. And usually I don't do this in CS2. I do this as an extra topic in an honors version of like discrete math or CS3. In CS3, but I'm not doing CS3 next semester or next year. Otherwise, I would assign this as usually assign this as a programming assignment. Where you're going to break a public key crypto system. So I'm just giving you a very, very high level introduction to public key cryptography and the RSA crypto system in particular. The idea here is that you're trying to communicate over an unsecure channel. So usually the actors that we have here are Alice and Bob, and they're trying to communicate back and forth. However, Alice's message is being sent, why Alice and Bob, by the way? A, B, right? And Alice is trying to send this message through an unsecured channel where somebody like an eavesdropper like Oscar can listen in. And so if Alice were to send launch codes 1, 2, 3, 4 in plain text, anybody who is listening in on this channel can go ahead and receive this. And if you think that that's not a problem, then it most definitely is. In fact, you can download a utility called Wireshark, and you can everything is wireless now, right? It's all going over 802.11, whatever, right? And you can download an application called Wireshark, and you can sit there and listen to all of the traffic going over the Wi-Fi. And if it's being sent in plain text, you can see, oh, the person with IP address 1234 is trying to access Reddit and this Reddit page on, et cetera, et cetera. You can see this exactly what's going on. And if data, for example, like secure data, like passwords are being sent over, then you can capture all those packets, right? And it's really, really easy. I mean, there are apps to do this, right? So the idea here is that Alice needs to encrypt first. So what we're going to do is we're going to take Alice and move her over here just a little bit. And what she's going to do is she's going to encrypt it using some sort of encryption function with a key K. So this is encryption with a key K, right? And as long as Bob over here has that key, you can go ahead and decrypt it, right? So he'll send it through a decryption function using the same key, right? And the same key. And basically these are inverses of each other. If you encrypt it and it ends up being 1, 2, 3, 4, you decrypt it and it should be whatever it was the original, right? So in other words, the encryption of a decryption of a number X should be X, right? So they're inverses of each other. If you apply the encryption and then the decryption, or the decryption and then the encryption, then you should recover the exact same number as before. That's the idea, okay? But the problem here, at least with this scenario that I've just depicted, is what? That Bob and Alice here have to get together at some point and share this key. And you've probably seen this depicted before where you do have these key parties, right? Where people get together and then they start sharing these predefined keys so that they can do one-to-one communication. And as long as that key is never, given out, right, then you're good to go. Nobody will ever, at least with modern encryption standards, nobody will ever find those things out. However, we have another scenario where Alice and Bob have never met before. Is it still possible for you to communicate with them? For example, Alice and Amazon. Bob is now Amazon instead of Bob being Bob. Alice wants to go to Amazon.com and ensure that all the encryption and their credit card, when they go to Amazon.com, is being sent securely, right? So, I didn't go to Amazon and physically exchange a key back and forth here. Instead, we're communicating here without any prior communication using what's called public key cryptography. So the idea is that Alice, or Bob, if she's trying to communicate to Bob, is that Bob should be able to, Bob should be able to have two keys, a public key right? And a private key. So that the public key, you can do encryption. But without the private key, you can't do decryption. Only Bob can decrypt messages that are intended for him. So that if this is a public key, all he has to do is say, here's my public key. You can go ahead and use that. Anybody can use that all they want. Encrypt their messages, send them to me, and only I, Bob, can decrypt them. Right? In fact, my usual go-to is Scott Chafin here. Let's go ahead and ask him. Does S. Chafin? No. Oh, I'm on CSE, right? Finger Chafin. Okay. More Etsy password. Prep Chafin. There he is. Okay. I don't know. What did I misspell it or something? Yeah, I did. There we go. So Scott is one of our sysadmins. And he regularly publishes this public key here. It's generated by PGP. It's a public key block, and it's just this huge random number, right? And you can use that huge random number if you need to in an probably an elliptical curve version of a public key crypto system, to encrypt a message and send it on to Scott here, Scott Chafin, right? Only he has the private key, right? He's not going to publish the private key. And that private key can be then used to decrypt stuff. So this is what a key looks like. It's just a huge random number, and this is a base 64 encoding of it. What I'm going to do today is I'm going to show you one such public key crypto system called RSA. RSA, there's nothing magic about it. It's just the first letter of the last name of the three people that came up with it. Revest, Shamir, and Adelson, or something like that. I forget what it is. In any case, I'm going to show you how it works. Before we do that, we need a little bit of modern algebra. So algebra, as in like A plus B is equal to C, that's not what we're talking about. We're talking about modern algebra, monoids, fields, group theory, et cetera, et cetera. I'm just going to show you a small subset of it first. Right? Z mod P. This is a set containing 0, 1, 2, 3, the integers 0 through P minus 1. Okay? And as long as P is a prime, this is what's called a field. Everything in this is going to have a additive identity and and a multiplicative inverse. So don't worry about that. I'll show you an example. Right? So let's choose something that's not a prime, say 6. This has numbers 0, 1, 2, 3, 4, and 5. Now, multiplication and addition over this group is going to be well-defined, you understand it. All you need to do is apply a modulus at the end. So, for example, if I take A plus B, with A and B being members of this thing up here, then that's going to be A plus B mod 6. So, for example, 1 plus 3 mod 6. What's the result of that? Well, 4, but 4 is less than 6, so it stays 4. In other words, if I take any two A and B, I end up with a C that's still in this set. We call that closure. Right? As long as you are staying within this domain, then you are within this set or field or group or whatever it is. Right? But now let's take something else. For example, say 4 plus 5 mod 6. Well, this is equal to 9 mod 6, but remember that 9 is not in this set here. So when you apply the modulus here, what's the remainder? We all know what mod is, right? In code, x mod 6. Right? It's just taking the remainder. So when you take 9 divided by 6, what's the remainder? 3. And you are right back in this set. Right? Now, an inverse is where you can take an A and multiply it by its inverse and recover 1. Okay? Now, this is well known here with real numbers, right? If I say A inverse, what is that equal to? 1 divided by A. And so A times 1 divided by A gives you 1. That doesn't work when you're when you're over like a group or a field like this. For example, what you have to do generally, well, let's just brute force it, for example. 0 doesn't have a multiplicative inverse. 1 is always its own inverse. Right? What about 3 here? 3 times what is equal to mod 6 is equal to, actually, yeah, we'll go with this, is equal to 1. Let's try. What about 1? Does that work? 1 times 3 times 1 is not equal to 1. Okay, what about 2? Nope. 2 times 3 mod 6 is going to be 0. Okay. What about 3? It could be that 3 is its own inverse. 3 times 3 mod 6, we already saw that. 9 mod 6 is 3. That's not it. Right. What about 4? No, we're back to 0. Do you start seeing a pattern here? 0, 3, 0, 3, 0, 3. Keep trying. Go to 5. 15. Mod 6 is going to be 3. We're back to 3. What is it about 3 and 6 that you can kind of tell something's going on there? 3 divides 6, right? They're not relatively prime. Okay. So let's try something else. What about 5? 5 times what is equal to 1 mod 6? Right? Well, I'm just going to go ahead and skip ahead here. 5. It's its own inverse. 5 times 5 is 25. Mod 6 is going to be what? 1. Right? So 5 is its own inverse. Right? The inverse of 5 is equal to 5. Okay? That only works if it's relatively prime to whatever you're looking at here. 5 is prime. 6 is not prime, but they are relatively prime. 5 does not divide 6. 6 does not divide 5. So that's why we like prime numbers. If I make this into a prime, everything is relatively prime to it. Let's check it out with 7. 0, 1, 2, 3, 4, 5, and 6. Right? Now what are some multiplicative inverses? 1 is always its multiplicative inverse. 0 never has a multiplicative inverse. What about 2? 2 times what? Mod 7 is equal to 1. All right, 2 times itself? Nope, that's 4. 2 times 3 is 6. Mod 7, that's not 1. 2 times 4, that's 8. Mod 7 is equal to 1. So 2 times 4. And also, 4 times 2, mod 7, is equal to 1. They're multiplicative inverses of each other. Okay? What else? 3 times what is equal to 1? Mod 7. 3 times 3? Nope. 3 times 4, we already know that that's 2's multiplicative inverse. So 5? 5. And now they're inverses of each other. What about 6? It's the only one that's left, right? Is that right? 2, 3, 4, 5, 6. 6 times 6, mod 7. Right? 36 mod 7 is going to be 1. Right? So those are all the multiplicative inverses. Now, what happens when you make this a really, really, really big prime? Right? That is going to give us a sufficient number of numbers in order to start encrypting things. Right? So here's the setup for the RSA cryptosystem. It's all based on finding inverses of these things and making sure that nobody else can find the inverses of these things. So at this point I need to consult my notes. There we go. All right, so 1, we're going to choose 2 large primes. Now typically these prime numbers are going to be like 2,000 bits, right? Which are very, very large numbers because you can represent up to 2 to the 2,000 a value that big, okay? And we're going to call these P and Q. 2, we're going to compute N to be P times Q, okay? That's pretty easy. Now, these are large numbers, but multiplying large numbers together is still really simple, okay? And then 3, we're going to compute Euler's totient function. Don't worry about it. the totient function of n is simply just p minus 1 times q minus 1. Very, very large numbers, you could still go ahead and subtract 1, right? That's pretty easy. And multiplying two very large numbers, well, you already did it up here. You might as well do it again a second time. Now, in general, the totient function is actually difficult to compute. It's only very easy to compute here because of the way that I constructed n. I chose these two prime numbers. And so all I need to do is subtract 1. It works out this way in the formula. But otherwise, what you would need to do is you would need to if you wanted to compute Euler's totient function, you would need to factor out all the factors of n and then put it through this, this formula. And basically what it's doing is it's counting the number of elements that are relatively prime to n. Right? But we know what that is automatically from Euler. Okay? Then what we're going to do is we're going to choose a number a such that it's between 2 and the totient value. And there we go. And that the GCD of a and the totient is 1. GCD being greatest common divisor, this just simply means that a and the totient are relatively prime. A does not divide this totient. If you randomly choose an a and its GCD is not 1, choose differently. Right? Choose a new one, choose a new one, choose a new one. In practice, what we're going to do is we're going to choose that a being 65537, I think it is. Is my memory great? 65537, awesome. My memory is pretty good today. Right? Now, why did we do that? Guess what? It's prime. Right? It's a small prime with only a few 1 bits. And it turns out in practice that's really nice. But if you choose something that's prime, then of course its GCD with anything else is going to be 1 because it's prime. All right, 5. Compute b, which is going to be the inverse of a mod the totient. And this is where the inverses come in, right? And that's why I just showed that little tiny exercise. If I were doing this in like a computer science 3 course or something like that, we would go into a lot more detail on modulus and modern algebra and stuff like that. But otherwise, just know that b is going to be the inverse of this. Why? Because we're going to encrypt something, we'd better be able to decrypt it. If we're going to encrypt it using this a here, we'd better be able to find an inverse of a so that we can take it back and decrypt it. Because that's what we're going to do. Here's my encryption function. Suppose that Alice, Bob, whoever, X is a message. It's just a number that's been encoded as an integer. And what we're going to do is we're going to take X and raise it to the power a mod n. Okay? And then the decryption here of y, that gives us y, is going to be y raised to the b mod n. Oops. Mod n. All right? Now remember that the decryption and the encryption should be inverses of each other. Now, this is way oversimplification. We actually need Fermat's little theorem to prove this. But let me show you what I mean. The encryption of the decryption, or the decryption of the encryption, let's do it that way. The decryption of the encryption of x should equal to x. All right? Let's find out if it does by applying these two definitions. Well, first of all, what is the decryption of the encryption? Well, this is going to be x raised to the a mod n. Right, there we go. Now apply the decryption definition here. And what I mean is I'm simply going to just take this. This is a. Sorry, that looks like 9. A. And I'm going to plug that in over here for y and see what I get. So the decryption is going to end up being x raised to the a raised to the b mod n. Now remember, what are a and b's? This is equal to x a times b mod n. But b was what by definition? The inverse of a. So this is x a A inverse mod n. Now again, for Mohs little theorem, you need to prove that this actually holds, but this is going to end up being x. Right? So if you encrypt it, then decrypt it, you should get back x, and you do. All right? So let's go ahead and walk through a Python implementation of this. Now I've chosen two large primes here to be 17 and 19. Right? That's not at all secure. I computed n here to be the multiplication of them. I've got my Euler totient function here, p minus 1, q minus 1 multiplied together. Then I choose, choose an A relatively prime to the totient. This is the standard prime that's used in practice. Why? Because it only has a few 1 bits. If I were to convert this over to binary, let's go to Wolfram Alpha here, to binary, you'll see that it only has actually 2 bits, right? So all the operations involved with this are going to be very, very efficient, right? Because it only has 2 1 bits. But also, guess what? Is prime? Question mark? Yes, it is. It is a prime number. So it's going to be relatively primed regardless of what p and q I choose here. Now I'm going to compute b, which should be a inverse mod the totient. I've got an external function to do that over here in my Euclid library. Right? I had to write it inverse mod. Right? Don't worry about it. It's an extended Euclidean GCD algorithm. Again, if this were a full CS3 course, we would be going over this. In fact, we would have gone over this in like a previous module, in fact. Right? There's my public key. All Bob has to do is say, all right, anybody that wants to talk to me, here's my A and here's my N. Here's the private key, P, Q, B, and N. Why? Because anybody with this private key can decrypt messages. All you need to encrypt are A and N, because it's going to be A raised to whatever X raised to A mod N. Now, before we actually go and encrypt a message here, why is it important that this private key be kept private? Right? And in fact, more importantly, how could we break this public key crypto system? How could I find P, Q, B, and N just given A and N? Right? Ideas. Well, in order to find B, I would have to find, to compute B here, that's going to be A and then the totient, so I would need P and Q. So that's not going to work. How can I find P and Q given N, though? Factor it, right? So simple enough? No, the best known factoring algorithms are going to be exponential. And if we choose very, very large numbers, thousands of bits, it's not going to be possible. And I'll show that to you here in a second. But otherwise, if it's just 17 and 19, what is 17 and 19 times 19? There we go. It's going to end up being 323. 323. Hey, Wolfram Alpha, please factor 323. There, it'll do it. But is it going to factor that? Oh, it did. Darn it. I must have chosen. Oh, no, it didn't. There we go. Factorization, computation, yeah. All right, it's just going to refuse and not tell me that it's, okay, there it is, thank you. All right, finally. Standard computation time exceeded. There we go. Thankfully, my faith in the computing world is restored, right? That this would take literally centuries or millions of years in order to do this, right? If I just chose a random large number that was composed of 2 primes, finding those 2 primes is going to be exceptionally difficult. But if it's only 17 and 19, then we're good, right? Let's see it in action here. So I've got a message here. My question is, do you like turtles? Yes or no? So let's go ahead and encrypt the message here. Just why? Right? Well, as a matter of practicality, we can't just encrypt letters. So what I'm doing here is I'm converting my string into a number, right? I'm encoding it as a bunch of bytes. And then I'm converting those bytes into an integer using what's called Big Endian. the most significant bit is at the left. In other words, what we would think of. If I say 1,234, that's the most significant bit or digit at the end, right? At the beginning of it. Then we're going to verify that in fact it is not too big to encrypt. If any x exceeds n here, then we can't encrypt it because it would roll around, right? Because it's basically overflow, right? If n is 52, then I can't encrypt 87 because I'm modding out by 52, and I would lose information there. So that's just a sanity check right there. And then I'm going to show you how you can take the message that's going to be encrypted into a number. Then the encryption here is simply going to be x raised to the power a mod n. Right? That's the encryption that we came up with. And then I'm going to print out what it's been encrypted as a number. Then we're going to try to convert our encrypted number back into a string. And what I've done here is I've padded it out to 256 bytes. So there's going to be a lot of leading zeros here, but that's just so that we can see it. Right? And then I print it out in one of two ways. First of all, I print it out as just text so that we can maybe read it. It's going to be garbage. And then I output it as a bunch of hexadecimal numbers, like you would see here. This is not hex, this is base 64, but it's the same basic idea. Right? It's just an encoding. So now let's run this, Python, RSA.py. There we go. So y is, if you look up the ASCII text value, it's 89. And the encryption of 89 goes to 174. 174 is not a printable ASCII text character, so we end up not printing it. But you can see that it's AE right here. AE in hexadecimal converted over to decimal. AE, so 0x AE to decimal. In fact, should be 174. Right? There are lots of padded zeros here because, like I said, I made it into a 256 bytes. Okay? But after the decryption here of going in reverse, y raised to the b mod n, then changing those bytes into a number, changing that number into a bytes, and then changing those bytes into a text, we recover the message y here, y. Now, let me show you again here some other examples. What if I said, yes, I do? All right, there we go. Now, my numbers here, 17 and 19, are way too small to encrypt this entire message with one encryption. Where's my message? There we go. Right? This would be a number that would exceed whatever it was, 200 and something. Let's go ahead and run it, and I'll show you. Error, you cannot encrypt this large number because that large number there is greater than 323. Right? This is my message. It's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bytes. But those 11 bytes are going to end up being 88 bits. And 88 bits, that's a really large number. It's not huge, but it's way more than 323. All right? So I'm not going to be able to encrypt that. So let's pump this up. Give me a 100-digit prime. All right, there we go. Random prime with 100 digits. Thank you, Wolfram Alpha. All right. And I'll come up here and I'll replace my 17. And I'll replace my 19 with another call to this. All right. Random 100-digit. Let's make it something different. 120-digit prime. Generally, you want to make them roughly equal in practice, but there we go. There we go. There. Two very, very large numbers. Let me actually print out what n is when I encrypt this stuff. There we go. Let's go ahead and kill that, and let's come up here. Yes, I do. Here's my n. I'll ask, Wolfram Alpha just generated those two primes, right? So Wolfram Alpha should be able to factor the product of those two primes, right? Oops, you've exceeded the maximum number of characters. Oh, wow. I can't even put in that many characters in Wolfram Alpha. It's not going to let me do that, unless I probably pay for it. And it's just it's a subscription service. Anyway, yes, I do is now this number. Encrypted is this other huge number. And when I try to encode that as text, what do I get? Random garbage. Right? So this is what Alice sends over the wire, random garbage, to Bob And Bob can go ahead and recover that at the end and get back the message, yes, I do like turtles. Right? Is that too old of a meme? I like turtles? The I like turtle kid? Okay. Yeah, you need to go into your meme history museum then, right, and find out what I like turtles is. Anyway, this is actually used in practice, right? Now, here's Scott's GPG, which is GNU's privacy tools or something like that. It used to be GPG, General, this is pretty good, this is pretty good privacy tools. That's what it is. Pretty good privacy tools. This is probably using some sort of elliptical curve cryptography. Same basic principle, but different mathematics behind it, right? Let me show you that RSA is actually used, right? So for example, let me go back to that Amazon.com. If you come up here to this little lock right here, you'll see that it's actually using HTTPS. Right? It's a secure connection. Tell me about it, right? Give me some more information. If I come over here, right? It's kind of hard to see here, but can I increase the size? No, I cannot. Nope, I can't do that either. All right, so TLS is Transport Layer Security. AES is American Encryption Standard. It's a block cipher. It's something else. 128-bit key for that cipher. Galois counter mode, SHA-256, ... et cetera, et cetera, et cetera. So it's using very, very complex suite of encryption standards here. If I were to actually view the certificate, it's been signed by, well, who is this? Oh, Amazon.com is their own signature, so they're self-signing stuff. Otherwise, there would be somebody else right here. There are several what are called certificate authorities. These are companies that generate these random numbers and then register them. And whenever you go to Amazon.com, then your browser goes over to that certificate authority and says, Amazon.com, here's their signature. Can you verify it for me? And they say, yes, we can verify that using, guess what? RSA, right? At least in this case. Hey, what is that thing right there? A big giant random number that is the modulus. That's your n. You could take this and try to decrypt this. Good luck, right? It's going to take you centuries or thousands or millions of years. But there it is. It's publicly available. Anybody else can communicate with Amazon or at least verify their signature here using this public key crypto system that is being published by them. Right? What else is there? Yep. Oh, okay, there's the actual signature algorithm. At least for this one, it's SHA-256 and ECDCA is for elliptical curve Diffie-Hellman key exchange, something, something, something. Right? So it's not actually RSA, but this one up here is RSA. And ooh, look at that key size. How big is it? 2,048 bit numbers, or 2,048 bits, which means that the two primes that were used to generate it were 1,024 bits. Right? We only had 100 digits. Right? How many is that in bits? Log base 2 of 100 is going to be actually like 10 to the 100. That's what it should be. 332 bits. So the ones that are used in practice are even larger, 3 or 4 times as large, right, as the ones I just used. Here's another nice demonstration. Here we go. OpenSSL. So I'm communicating with the CSE server, in particular with, let me see, 443. Does anybody know what port 443 is? You've seen ports before already this semester, right? When you connected to MySQL, what port did I tell you to use? 8601. No, it's not 8601. What is it? What is the MySQL port? What was it? It was the default, so maybe you never changed it. MySQL port number. What is it? That's not it. It's not 33. Is it 13306? That doesn't sound right. What is the default MySQL port number? Oh, it's 3306. There we go. 3306. Right. So what's the port number 443? It's HTTPS. SSH would be, I think, 23. Right? Very close. But this is going to be HTTPS. I'm communicating with its web server, right? Using https cse.unl.edu. There it is, right? And basically what I'm doing over here is I'm asking it, how do I communicate with you securely, right? Because there's this initial handshake here, right? Let me go all the way to the top here. And there's their certificate, right? I think that's self-signed. Yeah. Or no, some user, I don't know who they are, but they're in New Jersey. Some company, maybe in common RSA server, certificate authority 2. I don't know who that is. But then under that, then we've got University of Nebraska, Lincoln. Basically, the UNL is responsible for signing their own certificates. We're not, because they don't want to pay somebody like GoDaddy or something like that to generate certificates. But there's their certificate, really long, big, giant, random number, right? There's another certificate, there's the other certificates. There we go. So how do I communicate with you? What's the best way of communicating with you, CSE server? Well, first of all, you need to use TLS, Transport Layer Security version 1.3. Anything lower is considered insecure because there are bugs or flaws in those systems, those versions that have been exposed. Right? It's using Transport AES 256, Galois SHA 384 here as its encryption standard going back and forth. There's a session ID. And there's the ticket, right? Once we've set up this initial handshake and agreed how we're going to communicate, we've exchanged keys, and we go with this key here. Write it down because you don't have to write it down. you can't eavesdrop on my communication because it was only good for this one session. After that, nope, we'll generate a new one each and every single time. This is why it's extremely difficult. Mathematically, it's impossible to break this stuff. That's why you need to circumvent it, right? You need to find flaws in the system or flaws in the implementation because there ain't no flaws in the mathematics, trust me. Right? What else? And here's another one. That's our back and forth ticket. Let me show you another tool here called Nmap. And basically what it's going to do is it's going to scan all of cse.unl.edu for open ports and then ask, how do I communicate with you? Port 442 or 443 or whatever. There we go, it was done. Right, let's go all the way to the top here and see what kind of communication we can do. Port 22 is SSH, I was wrong, it was not 23. 25, I'm not sure what that is. What is port 25? Standard port numbers 25. FTP maybe? List of TCP and IP ports. Where's 25? 25, it looks, oh, SMTP. That's how you send email, right? So if you want to send email over to CSE and either bounce it off because you're a spammer and you want to make it look like you're, or a scammer and trying to make it look like it came from CSE, you could go ahead and communicate with port 25. Oh, it was right there, I should have looked. SMTP, Simple Mail Transfer Protocol. You can communicate with it using versions 1, 1.1, 1.2. All of them are insecure and considered insecure, but it still allows you to do it. And hey, there's RSA. RSA is a choice. It's not the best choice, but it is a choice. Right? What else do we have here? Oh, port 78. I don't know why they have port 78 open, but it's for finger. That's for, like, you can finger somebody and say, who are you, right? And that's what I was doing with Scott. I was pointing a finger at him to see what his messages were or what his public key was. There's HTTP over the traditional port 80. In other words, web traffic, but with no encryption at all. Right? That's why it's not listing any encryption here. RPC bind, I forget what RPC is. What is RPC? RPC. Remote procedure call. Right? I'm not, but that's also unencrypted. IMAP, the thing that I'm running, was running on port 143. There it is, 443 again. Right? There's our web traffic, HTTPS. Right? And it's open, and it does allow you to communicate with versions 1, versions 1.1, and below. If you did that though, and I was running Wireshark, I could probably decrypt even though you had encrypted stuff, I could probably go ahead and poke holes into it and find, as long as you communicated long enough and I captured enough packets, I could probably decrypt that stuff. Right? But over here with 1.3, isn't it? Yeah, 1.3, probably safe. I'm not sure what AKE is. Cha-cha is a hash code, or a hash function, a cryptographic hash function. But let's take a look at what else is supported here. Diffie-Hellman key exchange with RSA protocol using AES, American Encryption Standard, with 128-bit keys. That's supported if you wanted to do that. Otherwise, I think Camellia? I think that's a Japanese encryption standard. Otherwise, AES all over the place here. Sometimes with RSA, sometimes with elliptical curve. But otherwise, the preferred mode of communication here is very, very small, right? This is going to be AES, either 128-bit or 256-bit, and then you're using elliptical curve Diffie-Hellman key exchange. You're not using RSA. It's still considered secure, but it's not considered as robust and secure as elliptical curve, which is based on different math, the discrete log problem. Right? I wonder what SMTPS. That's secure mail transfer protocol. So that's encrypted email. Right there. What is submission? 587? 587. Email submission. Okay, that's just another SMTP server. I don't know why it's separate, but whatever. Maybe forwarding or something. IMAPS at 993, and it looks like that's all. Everything else is firewalled out, or doesn't have anything listening on it. Right? Let me try something else. Telnet to cse.unl.edu. Port, I don't know, 80. Are you listening? Telnet. Port 80. cse.unl.edu. Okay, how do I do it? I forget. Telnet? How do I specify the port? Darn it, what is it? Telnet. Telnet is just okay, it's just a space. Okay, so telnet, cse.unl.edu on port 80. What I'm about to do is open up a network connection to the CSE server on port 80, which is just that HTTP with no encryption whatsoever. We're talking, right? It's sitting there waiting for me to say something, right? And if I just say hello, right, that ain't gonna work, right? It doesn't understand what you're saying. Your browser sent a request that this server could not understand. So what you would end up having to do is something like, I don't know, get index.html. Nope, that's a bad server. Am I going to be able to do this in 5 minutes? Let's see. I'm going to have to look it up. I forget how to do it. No. Okay, there we go. So I got to quickly do this. Index.html, HTTP 1.1, and host. It was too long. All right. Get index.html, HTTP 1.1. Oh, come on, really? You're not going to let me do it? All right, if I cut and paste all of this then? Fine. Darn it. It's not going to let me do it. Instead, let's do something else. Let's send an email. All right, so what is it going to be? So telnet to what was that SMTP again? Come on. It was 25. So let's telnet into port 25 here. Oh, telnet cse.unl.edu 25. There we go. All right, now I can go ahead and say hello. All right, this is the protocol for sending email. Hello, cse.unl.edu. All right. Yeah. Pleased to meet you. Right, now we're talking back and forth. Right? I can communicate to the server. What I want to do is I want to send some mail from not phishing at notphishing.com. There we go. Oh, come on. Oh, darn it. Okay. Why did I put... come on. Kill it. Kill it. Kill it. Kill it. All right. End. Bye. Or quit. There we go. All right. Hello. And it's HELO, not HELLO. CSE.unl.edu. Hello. Pleased to meet you. And I want to send some mail. So mail from, say, Seberg at notfish.com. There we go. Okay, yeah, that's fine. I'll go ahead and send that for you. And let's go ahead and send it to, so RCPT2. All right, who wants to volunteer to be the guinea pig and receive this mail? All right, what's your Husker's email? Let's do that. .com, or not, .edu, right? There we go. All right, there we go. Oh, it does not exist. Oh, okay. We're still good though, right? They just checked my domain and it doesn't exist. And say, okay, data. All right. There we go. Oh, come on. All right, I'm not going to be able to do not fish. All right, you get the idea though. Right, that this is why we write email clients to do all this automated stuff for us, and then just have a bunch of boxes that we type stuff into, because you can this back and forth can actually get quite. Come on, quit. There we go, quit. All right. Do I have an example that I can just send really quick? No, I don't. Darn it. And then it ends with a period, and then you say quit, and it sends it on. I'm not a good enough typer to do this in the next 3 minutes, but you get the idea. You're not going to get that email. I don't know. The completeness in me really wants to get this done. Hello, cse.unl.edu. Okay, so mail from. I'll just go with Seberg. Somebody actually legitimate here. There we go. And RCPT2. And you said Z Kozak? 2 at huskers.edu. Oh, is it? Oh, okay. It'll probably still forward. I don't know. Anyway. Let's go ahead and go with from Bob, right, to, oh, come on. Oh, data now, right? All right, blah, 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 blah. Right. There, you might get something with just a mashed keyboard here. There we go. Message accepted for delivery, and then we'll go ahead and say quit, and then it says goodbye. So let me know if you ever get that. It probably is going to end up getting bounced by the UNL servers saying this is not, it's not going to have the necessary headers or back and forth or security or anything like that, because it's just, it's just a stupid mail. Oh, was there an error? Message accepted for delivery. I don't know why you would gripe about it, but whatever. Anyway, anything that? Probably not. All right, darn it. Anyway. That's how it works behind the scenes. Of course, it would be encrypted if you used a different port. And it was just an extra fun thing to do today. On Wednesday, we'll have a course retrospective. Friday, nothing.